It's a pleasure for me to be here to have the possibility to present my work. And everything I will talk about today is about joint works with Laszlo Erdős and Dominik Schröder. And in particular, I will report on the fluctuation in the spectrum of non-Hermitian matrices, which have independent identically distributed entries. First of all, I will start with a very brief introduction. Sure. Yeah. Thanks. So, as I said, I will start with a very short introduction about random matrices and the problem I will talk about. So this goes back to the 50s when Eugene Wigner had the big vision that local statistics of large quantum systems exhibit a universal behavior. Additionally, doesn't work? Yes. So additionally, he also suggested large Hermitian random matrices as a mathematical model to observe this phenomenon. However, today I will talk about non-Hermitian matrices that in general are much less studied, but similar universal behavior are expected. And as I said, all the results that I will present are about non-Hermitian matrices. However, I will discuss this result and introduce the model in comparison with Hermitian matrices to compare these two different ensembles. So just to set the notation, I will start with the Hermitian matrices that for the rest of the talk will be denoted by H. So here H is an n by n matrix with IID entries that are not necessarily Gaussian. So on the entries, we assume that are standard random variables with variance 1 over n, and then we assume that all the moments are finite. And as the size of, since Wigner is known that as the size of the matrix goes to infinity, then the empirical distribution of the eigenvalues converges to the Wigner semicircular law. And I will say a few more things about this in the next slide. And instead, I will denote non-Hermitian matrices by X, and X here is, again, an n by n matrix, and the entries are ID random variables like in the previous case. We just drop the Hermitian condition. And also in this case, as the size of the matrix goes to infinity, the empirical distribution converges to a deterministic measure that in this case is supported on the complex plane and is the so-called circular law. So in this slide, I want to discuss which are the main questions that we are interested in for random matrices with non-Gaussian entries. So the table is divided as follows. So horizontally, you can see there are 3 different lines that from the top to the bottom are 3 different questions in order for increasing level of difficulties that one would like to ask. And vertically, instead, is divided according to the matrix to being Hermitian or non-Hermitian. And I apologize that here in each block I just wrote the name for the first result in each of these blocks, but many other people contributed to these problems, and I hope that I didn't forget anyone in the list at the bottom on the slide. And all these results are either like partial previous result or some extension and generalization. So I will start with the first question, that is the density of states. So as I already mentioned in the previous slide, if you have a bunch of eigenvalues, you look at the empirical distribution, and then you want to prove that this converges to some deterministic measure. So a sort of law of large number type result. And as I already said, this deterministic measure is given by the semicircular law in the Hermitian case and by the circular law in the non-Hermitian case. Then the next natural question is to study the fluctuation around this deterministic limit. So to do so, we look at the linear statistics, that is the sum over all the eigenvalue of f evaluated on these eigenvalues, where f is just a nice test function that is order 1. And so this summation is typically an order n quantity, since we have n eigenvalues and f it's an order 1 quantity. And then we subtract the expectation, that is also an order n quantity. And I claim that this difference converges to an order 1 Gaussian random variable. So before proceeding, I want to stress about the scaling here, because usually from a standard central limit theorem, you would expect that the difference of 2 order n quantities will fluctuate on a square root of n scale. Instead, in this case, I claim that this difference it fluctuates on a much smaller scale that is order 1, and is a consequence of the strong correlation of the eigenvalues. And this result has been proven about 13 years ago for Hermitian matrices, and quite recently, we proved that the central limit theorem for central linear statistics holds for non-Hermitian matrices and quite generic test functions. And lastly, I want to comment about this universality phenomenon that is the one that Wigner predicted. So that we look at a finite number of eigenvalues as a point process, and we want to compute the distribution of these local statistics. And the very interesting feature here is that the local statistics are independent of the details, in the sense that the local statistics depend only on the fact that the entries of the matrix are either real or complex random variable, but it does not depend on the distribution of the entries. And this conjecture for Hermitian matrices has been proven about 10 years ago, and it's been proven that the distribution is not neither Gaussian nor Poisson, but is given by the Wigner-Dyson statistics in the bulk and the Tracy-Widom at the edge. And I will say a few more things in the next slide. And as I said at the beginning of the talk, it is expected that such universal phenomena also hold for non-Hermitian matrices. And this is what we proved recently for the eigenvalues close to the edge, so close to the unit circle. So you can think about this result as the non-Hermitian analog of the Tracy-Widom universality for Hermitian matrices. And instead, proving universality in the bulk for non-Hermitian matrices is still a major open problem in the field. And I just want to quickly mention that the best result up to date is by Tao and Wu, where they proved that universality both at the edge and the bulk, but under the additional assumption that the first 4 moments of the entries match the Gaussian one. So this is the picture that I promised you earlier. So when we prove universality, it means that we zoom on the level spacing of the eigenvalues, that in this case is, is n to the minus 1 in the bulk and n to the minus 2/3 at the edge. And then we look at this finite number of eigenvalues and compute their joint distribution. And a similar question one can ask also for non-Hermitian matrices. And this time zooming on a scale n to the minus 1/2, because n to the minus 1/2 is the typical distance between eigenvalues in the non-Hermitian case. And this green regime that is close to the edge is where we proved that this universal conjecture is indeed true. And the purple regime is in the bulk, that is what I said, that is still an open problem. So now, in the remaining part of the talk, I just want to quickly explain why the analysis of non-Hermitian matrices is much harder compared to Hermitian matrices. And this is because of the resolvent, that in the non-Hermitian cases, it's very unstable. So let's start first with the Hermitian case. So here we look at the resolvent of H at a spectral parameter E plus I eta. And we have the following deterministic bound on the norm, so that the norm it deteriorates like 1 over eta. However, one can expect that the randomness of H helps to make it smaller, and this is indeed the case. One can prove that the resolvent entry-wise is bounded in this very strong sense. In the non-Hermitian case, instead, the situation is much worse because there is no way to regularize. There is no parameter that plays the roles of eta like in the Hermitian case. Indeed, if we look at the resolvent of X at the spectral parameter Z, when Z is in the unit disk, then there is no deterministic bound for this norm. This is basically infinity because Z could be very close to an eigenvalue. However, also in this case, we expect that the randomness helps and that entry-wise, after rescaling it properly, this quantity is bounded, but in a weaker sense. So that any moment that is strictly smaller than 2 should be bounded, and then the second moment diverges logarithmically. So how do we deal with this problem? And we circumvent this problem relying on Gierko's formula, as is introduced in the form introduced by Tao and Wu, that is an integral representation of the linear statistics of non-Hermitian eigenvalues that here are denoted by sigma in terms of 2 different spectral parameters, that here are Z and eta. So here, GZ is the resolvent of HZ, that is the so-called hermitization of X around the point Z. And before proceeding, I just want to comment about this integral representation. So you see that we have the resolvent GZ evaluated as spectral parameter I eta, and data is integrated from 0 to infinity. So in particular, I want to stress that in this formula, one needs to understand the resolvent even for very small eta close to 0. But why we are so happy about this formula, and this is because we started with linear statistics of non-Hermitian eigenvalues, and using Kirchhoff's formula, now we are back to the Hermitian world, because GZ is the resolvent of an Hermitian matrix. However, there is still a major difficulty, that is the Z dependence of the resolvent that is not there in the usual Hermitian case. And in particular, this Z dependence, it's hard, because we have to understand the joint distribution of the resolvent for different spectral parameters Z simultaneously. So this is the hardest part of this formula. And before moving to the last slide, I want to stress that actually even for fixed Z, the analysis of the resolvent is quite hard. Because, for example, when we prove edge universality, so for the eigenvalues close to the unit circle, we have to understand this resolvent GZ when Z is very close to the unit circle. And then from this animation, you can see that as Z approaches to absolute value 1, the limiting density of states of HZ develops a cusp singularity in 0. And this is a non-trivial fact to analyze when one looks at the resolvent. So lastly, in this last slide, I want to just flash which are the main techniques that we use to study this Kirchhoff's formula, just to give an idea. So here you can see that in Kirchhoff's formula, I divided the eta integral into 3 different regimes, and this is because each one of these regimes will be analyzed using very different techniques. So in the very small eta regime, so when eta is much smaller than n to the minus 1, then we would like to prove some kind of smoothing inequality, in the sense that to prove that the smallest eigenvalue of HZ, that I denoted by lambda 1z, it's the probability that this eigenvalue is much smaller than n to the minus 1, it's small, so it's smaller than n to the epsilon for some tiny epsilon. And technically, we prove this kind of result relying on rigorous supersymmetric analysis. Next, we have the microscopic regime. So when eta is basically proportional to n to the minus 1. And this regime is analyzed using weakly correlated Dyson-Brillouin motions. So here I just first wrote the DBM, Dyson-Brillouin motion for a fixed Z. But as I said, if we compute the K moment, or even like you can think that K is 2, we have to understand the correlation of this lambda Z for different Z1 and Z2. And the correlation is given as follows, where U, Z, and VZ are respectively the left and right singular vector of X minus Z. And for example, to prove the central limit theorem for non-Hermitian matrices that I mentioned earlier, we have to prove that this correlation is small as long as the point Z1 and Z2 are sufficiently far away from each other. And lastly, there is this purple regime that is the regime that involves the macroscopic and mesoscopic scale that is analyzed using resolvent method. And also in this case, I want to stress that yes, we use resolvent method, but it's not enough to use the usual local law for a single G. But again, we have to understand the correlation for different Z1 and Z2. And so we have to prove multi-resolvent local laws of the kind that I wrote on the slide. So like trace of GZ1, GZ2. So traces that involve the product of resolvent at different spectral parameters Z1 and Z2. So I hope that I gave you just a vague idea of the techniques and the idea we use, and thank you very much for your attention.
Hendrik, any question from the online audience?
I have no, I don't think so, no.
Okay. I guess everything was clear. I thank Giorgio again. Our next speaker is Raphael Ducatez from Uniform, a local. Thank you.
Should I put? Yes. Okay. Great. Yes, so good evening, everyone. I'm very happy to be here to talk about this subject. So this is a joint work with Johannes Halt and Antinors, who are working here in Geneva, and that's kind of just the reference for the paper that I will just present you very briefly here now. So just go quickly to the model. So we are considering the Erdős graphs. It's just the simplest random graph you can think of. So just take n vertices, and between each vertices, draw a coin with probability to add an edges or not. So P is basically the only parameters of the graph, and you write it like d over n with d the mean degree of the graph. So we will consider mostly when p goes to 0, so that means, that is the sparse regime. So consider the agency matrix of this graph, so just as a random matrix with 0 and 1 with kind of binary entry with parameters p. Question is, what can we say about this eigenvalue, eigenvector, etc.? So first, a very classical result that can go back from Wigner, actually, almost, or at least for the techniques, is that as soon as the mean degree of the graph converges to infinity as n goes to infinity, then we get the semicircle law. Well, we have to rescale A by the Gorex rescaling 1 over square root d, and then get it. So what does it mean? Like, this means like almost all the eigenvalue lies between -2 and 2, and more precisely that there is actually a little O of 1 eigenvalue outside. And so the goal of work is to give a more precise picture of this, and to say what can we say inside of the bulk, and if there is anything happens outside. So here, okay, so the graph on the left will be all our main result is summarized here. So the interesting behavior occurs in what we call the critical regime, is when d is proportional to log n, so and the size of the graph. And what's plotted on the left-hand side is the spectrum for each parameter of B. So between -2 and 2, there is always the semicircle law, where most of the eigenvalue lies. And for B large, so for a large degree, that's actually all the spectrum lies there, so no other eigenvalue. And one of the and our results say that the corresponding eigenvectors there are delocalized. And delocalized means that actually you can, in a very strong sense, that you can estimate. You can estimate the L-infinity norm of the eigenvector is almost optimal. Now, okay, I also mentioned some related work by Bourgade and other, and many other professors that have been mentioned in the previous talk. So that was for insides of the bulk. There is the other result I have to mention is the blue part in the left part is where there appearance of eigenvalues, but there are very few of them, and we get actually a one-to-one correspondence with large degree of the graph. So let me state it otherwise. for any, you look inside of the graph, and for any large degree of the graph, large degree means twice as large as the mean degree of the graph, there will be two eigenvalue, one positive, which is strictly larger than 2, and one kind of symmetric, strictly less than -2. And the fact is that there are only ones. There are the only ones there. And we can also say that the corresponding eigenvector of this eigenvalue actually concentrate around these large degree vertices. So they are not just one, but it could be just for a linear combination around some balls around this one. And previous work or similarities work, I have to mention, so Benet, Georges, Bordenave, Tikhonov, and Youssef. And third result, so about that, so still in the blue regions, we are able to improve our analysis at the edge. So, whatever. So at the very edge of the spectrum, the blue regions, we can prove that the eigenvalue statistic converges to Poisson law. And we have an explicit form of this Poisson process. Okay, so now some idea of the proof. Oh, no, sorry. Let me mention that I will just tell you what the B star is and how many eigenvalue there are in the blue region. So just a quick cultural point. So if you ever heard about the Erdős graph, you should know that there is a connectivity transition around log n, so that if D is less than log n, there exists some isolated points. And actually, this is like a more general formula phenomenon for D in the critical regime, is that it's processes there that we can see very large degree and very small degree. So if you choose any x's, you have like a large deviation principle, which is that the probability that we observe a large degree at that point is exponentially small, but exponentially in D. So if D is log n, then we just polynomially small. So if you take n vertices, so actually the number of large degree or number of very small degree will be a polynomial on n. And the h here, h of alpha, the large deviation function actually is very simple, explicit, is the same for the Poisson law. So this gives us, actually, we can compute the largest degree of the graph, and for the transition in the spectrum, so as from our previous results, as we state that large eigenvalue only comes from large degree. So the question is simply, are there any large degree or not, so larger than 2D? And it appears for D less than, so the B star, which is 1/2 log 2 in this one. So idea of the proof. So the main, so as we I would say guess that they are related to large degree vertices. So let's look at the Erdős graph locally, and the good approximations is to think of it as a regular tree. Well, I would say that Galton-Watson tree locally is like the natural approximation, but because here D is large, we can even very simplify it as so the degree as constant. And if we set the basis as a spherical vector on this vertex, one can easily see that such exercise, that the adjacency matrix of this regular tree is just simply given by the right tridiagonal infinite matrix with parameters alpha x. So I just forgot to define alpha x. It's dx divided by d. So just the mean degree. And once again, it's an easy exercise from this very simple tridiagonal matrix to calculate its spectrum. And if alpha is less than 2, then the spectrum is only -2 and 2. So no eigenvalue appear outside the bulk appearing there. And as soon as alpha x strictly larger than 2, there is two eigenvalue, one strictly larger than 2 and one strictly less than 2. That can be calculated explicitly. And moreover, well, it's also easy to get the eigenvector, which actually decay exponentially from 1. And if we're going back, so just forget that, don't forget that we use the basis, which is symmetric around the circular symmetric. So what we get is an eigenvector that decay exponentially and with a spherical symmetry around the center of the graph. So that's for the ideal regular tree. And to come back to the Erdős graph, so here we have to work a bit, but we can deal with all the probability error terms and of the irregularity in the graph. And the thing is that the Erdős graph locally is close enough to the ideal D graph such that we get the corresponding eigenvalue. So more precisely, we can just guess that the eigenvector will look like the one we get before, and with the eigenvalue lambda alpha x, and just calculate, plug it, and calculate the norm of what to get, and with good probability it will be small. And from this we obtain it directly that we have an eigenvalue close to this. So, and that can be done for any large degree vertex, and so we get the correspondence one-to-one to large eigenvalue and large degree. So one has to prove that there's only one, but okay, so that's kind of a tricky part, so I just say a few buzzwords. We use a moments method from the non-backtracking matrix. So we can't use directly moments method in the graph, so it just doesn't work for large L. But for the non-backtracking matrix, so the matrix which corresponding to a random walk, but where you're not allowed to coming back. So that's actually, so it's because you remember where it came from, so the B matrix is actually on the edge. Here we are able to calculate a very large moment and to get that the spectral radius of this matrix is bounded, and from this there is also machinery to say something about the spectrum, and to deduce that there is no other large eigenvalues than the one we just stated before from the large degree. And so very quickly, because I will just say a few words for the delocalization part. So that's kind of the method that has been mostly used by the teams around Erdős and yeah, so as in the previous talk. So the basic idea is to maximize the infinity norm of the eigenvector by the green functions. And the green function can be estimated by some local laws. So in one minute, just to very quickly take an overview of the methods, is to write some short complement formula for the green functions, and use this as a implicit definition of the G function. And here, I would say that the difficulty compared to what was done before is we work with a very sparse graph, and applying the usual method will not work, so we have to work on some restricted set of vertices. Use this self-consistent formula, and get that there is all machinery that we obtain to prove that actually as I said, the trace of the green function is close to the Stiegler's transform of the semi-cycle. And from this we get, as I said, the local law and the delocalization part. So thank you for your attention.
Okay. I was wondering whether there is whether the intensity of the in the semi-localized phase, the intensity of the Poisson process at the edge is depends on the sampling probability of the edges, and if this dependency is explicit.
So yes, we can compute the statistic of the fluctuation at the edge. So the density of the Poisson is explicit. It's just that, okay, so the prediction from the lambda of alpha x is too rough, actually. So we have to do a much more precise analysis of the Erdős graph around the large degree. And actually what came into play is the size of the, so of course the large degree, but also the size of the second sphere around the large degree. So you have a formula to get the eigenvalue from these two parameters, and it's also kind of easy to have what is the law of the large degree and what is the law of the fluctuation of the second sphere.
Okay. Another very quick question. I guess that the largest eigenvalue always in the semi-localized phase is not Tracy Widom.
No, it's Poisson here.
Okay.
It's
yes,
really Poisson.
But
So.
Okay. So it's yeah, sure. Sorry.
No, it's really more picture like in the Anderson model where you are at the edge, the localizations and the Poisson statistics.
Okay, thank you very much.
The next speaker is Dominik Schröder from ETH.
Okay. So first of all, yeah, it's a great pleasure to be here and to be able to speak and present these results. So today I want to talk about strong quantum unique ergodicity and thermalization for Wigner matrices. And what I present is two joint works with Giorgio Cipolloni, who just spoke, and Laszlo Erdős. So first, just to introduce the name quantum unique ergodicity a bit. Just a brief introduction to classical systems. So if you have a chaotic classical system, then you expect that you are on the right-hand side of this slide, namely that you have uniformly distributed eigenfunctions. And then in this general setup, there's a long history of quantum ergodicity and quantum unique ergodicity. Namely, you expect if you have the eigenfunctions of a Laplace-Bertrami operator, then you expect that the inner product of eigenfunctions with a pseudo-differential operator converges to delta ij times an integral over the symbol of the pseudo-differential operator. Then there's a long history. So this was first proven for most index pairs in the 70s and 80s. Then more recently, there have been analogous discrete versions for large regular graphs. And then there's the celebrated quantum unique ergodicity conjecture from the 90s, that this actually holds for all index pairs, and that's where the name comes from. Then there have been some special cases proven for arithmetic surfaces. And finally, I want to mention that there's a physics predictions for general systems saying something about the speed of convergence in this upper formula. Namely, it's expected that the variance of such a quadratic form is proportional to the local eigenvalue spacing, and this I will come back to. So this was just to introduce the terminology we use. So the model we use is the Wigner matrix. So as Giorgio already mentioned 2 talks ago, Eugene Wigner's vision was that the energy levels of a large quantum system can be modeled by the eigenvalues of a large random matrix, Wigner matrices. So a Wigner matrix for me is just an Hermitian random matrix, either real symmetric or complex Hermitian, whose entries are identically distributed up to the symmetry constraint and have mean 0 and all the same variance. And the variance 1 over n is just chosen in such a way that the spectrum is bounded. So this picture is what you already saw many times probably. So the global eigenvalue density of a Wigner matrix is the semicircular distribution between -2 and 2. So in the bulk, the local eigenvalue spacing is 1 over n. That's the local eigenvalue spacing from the previous slide. And then when you look at the microscopic details of the matrix, for example, you pick like the middle gap and rescale it by n, because that's the average size of the gap. And then you also rescale by the local density, and then plot the histogram, that's the right plot. Then you obtain a beautiful curve, which is very close to this explicit curve known as the Wigner surmise, and that's Wigner's universality conjecture. So Wigner observed or speculated that the gap statistics are very robust statistics. So if you change your system, if you add some global symmetry, or if you change something globally, then the semicircular distribution can change. But these gap statistics are something very robust, and basically the only thing which matters for the gap statistics is the symmetry class. So this is the Wigner-Dyson meta-universality conjecture, formulated in the 60s and then finally proven basically 10 years ago. So these are Wigner matrices, but today we don't want to talk about eigenvalues, but we want to talk about eigenvectors. So let me present the main result. So random matrices are expected to model chaotic quantum systems. Hence, the quantum unique ergodicity, as introduced on the first slide in the general setting, is expected to hold for Wigner matrices, and it is expected to hold with optimal speed. And this has been formulated also as the Eigenstate Thermalization hypothesis by Deutsch. And this is our first result. So let Ui be the orthonormal eigenvectors of a n by n Wigner matrix, and let A just be any deterministic observable matrix. And then the statement is that if you take the inner product of your eigenvectors with this deterministic observable matrix, then you obtain delta ij times the average trace of A up to an optimal error of order 1 over square root of n. And this is exactly what I said in the first slide, that the variance of this quadratic form is expected to be of order 1 over n. That's why you have the 1 over square root of n here. And then let me also mention, when A is a constant multiple of the identity, then of course this is trivial. Yeah, so what this tells you in essence is, if you have your eigenbasis Ui, and you multiply it by traceless observable, then you obtain something which is asymptotically orthogonal. So if you take 2 unit vectors in the sphere, which independently, then you exactly expect they have to be, that they have a scalar product of order 1 over square root of n. So in other words, this result just is that multiplying by a traceless observable makes the eigenbasis asymptotically orthogonal to itself. So that's the first result. And once you see a result like this, then of course the next question you may ask, is this bound optimal? And if it is optimal, can you identify the limit or the limiting distribution? And that's the second result, and the answer is yes. So here there's a caveat. Here this is only for bulk eigenvectors. So bulk eigenvectors means corresponding to an eigenvalue in the bulk of the spectrum. And the statement is, for any deterministic Hermitian observable with non-trivial Hilbert-Schmidt norm, we have a central limit theorem, in the sense that if we multiply this difference of the quadratic form with the trace by square root of n, then we converge to a standard Gaussian random variable. So that's the quantum unique ergodicity. So let me just give a brief history of related and previous results. So if your deterministic observable matrix is rank 1, then the statement we are looking for is basically equivalent to the complete delocalization of eigenvectors, just in Raphael's talk just now. So when you just take the inner product with any fixed deterministic vector q, then you expect this inner product to be of order 1 over square root of n, and this is has been established for a series of models, all using the resolvent method. The convergence in probability without convergence rate, this has been established before by Dyson-Brownian motion methods. And then there has been a series of works for basically finite rank observables. And also there's an independent result, which was basically published at the same time as ours, proving the Gaussianity in the case when A has intermediate rank. So not finite rank and not full rank, but intermediate rank. So rank between n to the epsilon and n to the 1 minus epsilon. And this is also DBM methods. So then finally, let me just use the last 5 minutes to give you like 2 flashes of the proof ingredients. And the proofs of these 2 theorems are basically independent or use independent methods. The first result, the Eigenstate Thermalization, this is a pure resolvent calculation. So again, the resolvent is just the typical resolvent, and we have a local law for the resolvent, in the sense that the average trace of the resolvent is something deterministic plus a small error. And why is this useful? It's useful because it allows you to locally resolve the eigenvalues at a scale just above the eigenvalue spacing. But today we are not interested in the eigenvalues, we're interested in the eigenvectors. So basically we need an analog of this local resolution of eigenvectors for the local resolution of the eigenvalues for the eigenvectors. And we also have something like this. So when you take some local sum of these quadratic forms of eigenvectors with the observable, then this is basically the same as a 2 resolvent trace. So this allows you to translate information on the trace of a product of 2 resolvents into information about the eigenvectors. So a single resolvent gives you eigenvalues, 2 resolvents give you eigenvectors. And then, so the core of the proof here is something which I cannot explain in this brief amount of time, but the core of the proof is really establishing that this product of 2 resolvents with traceless observables is basically in bounded quantity, and once you have this, you use this relation to conclude the optimal overlap bound of order n to the minus 1/2. So this is a sketch of this first theorem. And then the second theorem, this goes a very different route. So when you have your matrix and you add a small Gaussian component, then you can view this as a dynamical picture. So adding an increasing Gaussian component is equivalent to having an eigenvalue flow, which is the commonly known Dyson-Brownian motion, but it also induces a flow on the eigenvectors. And I wrote these 2 flows here. The first line is how the eigenvalues change under the flow, and this is independent of the eigenvectors. But then the eigenvectors also change, and they change depending on the eigenvalues, and they also have this Brownian motion here in the first term. So this is the eigenvector-eigenvalue flow. And under this flow, certain linear combinations of overlaps satisfy a discrete heat equation. And this goes back to a result by Bogart, Yao, and Yin from 2020. So for example, I just wrote here an example for the product of 2 overlaps. So when you have different I and j, then the off-diagonal overlap squared plus the I overlap times the j overlap, this is such a certain linear combination which satisfies a heat equation with a fractional Laplacian. And then you prove Gaussianity for the diagonal overlap, so we can only do the diagonal overlap after a short time, so the time is basically the local eigenvalue spacing and a little bit longer, in 3 steps. In the first step, we replace this fractional Laplacian by another operator which averages in every direction on the level of the Dirichlet form. Then we appeal to a recent result by Marcinek and Yao and use the energy method for Dyson-Brownian motion. And then finally, since we could replace the fractional Laplacian by something which averages in every direction, we are again in a position where we can use local laws for resolvent products in the last step. So this concludes the proof for the Gaussianity after a short time, and then in the last step one has to remove the Gaussian component in order to prove Gaussianity for the original overlap. But this is a fairly standard step using the Green's function comparison theorem. So this is the sketch of the proof for the second result. So let me just summarize. So the first result was an optimal bound on the overlap for general deterministic observables. And the second result was the Gaussian fluctuation of the overlap. And the main novel tool here was the multi-resolvent local law. And I don't have time to go into any of this, but multi-resolvent local laws are really the key for quite a few recent results on Wigner matrices and their generalizations. Let me just mention a few flash words. So the first would be thermalization, so the long time evolution of unitary evolutions. Then quenched universality. This is closer to Wigner's original universality vision. Then the mesoscopic CLT for non-Hermitian IID matrices, what Giorgio talked about half an hour ago. And then finally, functional CLTs, so CLTs beyond eigenvalues, but CLTs for, also involving eigenvectors. Okay, so with that, I would like to thank you for your attention.
Yes, thank you. Since your result on the distribution is only valid in the bulk, I was wondering if you are expecting any differences in the edge there, and what in general makes the proof more difficult there.
So we don't expect any differences at the edge. In fact, we have a result at the edge, but it requires a little bit of averaging. So we have a result if you take n to the epsilon eigenvectors at the edge and you take the average, then we can prove the Gaussianity. But simply the analysis of the Dyson-Brownian motion is much more involved at the edge, and we haven't done it yet. But we don't expect any surprises.
Okay. Thank you.
Any question from the online audience?
Sorry, no, online is not very active.
Well, it's late, I guess. Well, it's not late everywhere. Okay, thank you very much.
You.
Let's take the speaker again. Okay, good. Everyone is on time. Okay, our next speaker is Tobias Ried from Max Planck. Thank you.
So yeah, thank you very much for giving me the opportunity to present the universality of the magnetization ripple and some of the techniques, mathematical tools that go into the proof, and that is joint work with Radu Ignat from Toulouse, Felix Otto and Pablo Statsoulis from Leipzig. Here. So what I want to show you today is that the magnetization ripple is an interesting phenomenon, and it connects to many different fields in mathematics. So we want to address the universal character of an experimentally well-documented phenomenon from material sciences, which from a probabilistic point of view is interesting because it involves quenched disorder and quite naturally also involves non-Gaussian random fields that approximate white noise. From a variational point of view, we want to minimize a non-convex energy functional that actually turns out to be in need of a renormalization procedure. It connects to singular SPDEs because the Euler-Lagrange equation that describes the minimizers of the energy functional is a singular stochastic PDE. And in order to prove the coercivity of the energy functional, we actually rely on fluid mechanics tools, namely the Harman-Kobath-Monin identities for the inviscid-Burgers equation. And what I somehow want to convey today is that we are able to express the universality of the magnetization ripple through a rough path type strategy that is based on spectral gap inequality and gamma convergence techniques. So just briefly, what is the magnetization ripple? So the magnetization ripple is a microstructure that is formed by the magnetization in a thin film ferromagnetic material, and you can actually see an electron transmission micrograph picture of a ferromagnetic material with some larger magnetic structure and this ripply magnetization ripple on top of it. In experiments, it manifests itself through its characteristic texture that is always orthogonal to the average magnetization direction, as indicated here with the arrows. And it is triggered by the random orientation of the grains in a polycrystalline material. And for the rest of the talk, I want you to think of the polycrystallinity as being modeled by random tessellation of the plane when you throw in a random orientation in each of the cells. And the universal character that I want to express is that the magnetization ripple itself does not depend on the precise composition or the geometry of the polycrystalline material. Now, in order to introduce the model, one actually has to start within the micromagnetics model, which was derived by Landau and Lifshitz. But actually, when you go to the to an effective description using that you are actually talking about a thin film ferromagnetic material, Ignat and Otto derived or proposed the following reduced energy functional, which is an energy functional for the transversal magnetization component U, which for simplicity we assume to be one periodic. So instead of working in the plane, we simplify our life a bit and look at functions on the torus, which due to the non-local stray field energy that the magnetization creates and interacts with it, has to be a vanishing average in the x1 direction. And then the total energy functional that we want to minimize has an exchange term d1u squared, a term that comes from the non-local stray field interaction, and a term that effectively looks like the interaction with a magnetic field, which comes from the polycrystallinity, and Xi here is the effective influence of the polycrystallinity on the transversal magnetization component, and it's modeled by a random transversal field, which you can think of white noise, and actually on large scales, it is expected to be of white noise character. The constant sigma here is just to model the strength of the field, and again, I want you to think of the noise as coming from this random orientations in a random tessellation of the plane model. So it's quite natural to consider classes of non-Gaussian approximations of white noise, and that is why we want to consider the following class of probability measures that are the distributions of our noise Xi. Namely, we want to consider probability measures on periodic Schwarz distributions that are centered, stationary, satisfy some symmetry property, namely that the law is invariant under reflection, say along the x1 direction. And most importantly, we want to assume that our probability measure, which I always denote by brackets, satisfies the spectral gap inequality, saying that if you look at a nonlinear function of the noise, then its variance can be controlled by the expectation of the L2 norm of the derivative of that functional with respect to the noise. It turns out actually that this L2 type version of the spectral gap inequality also implies an LP version for any p strictly less than infinity, and therefore you can think of it as a replacement for Gaussian calculus, which we don't have at our hands because our random variables are not assumed a priori to be Gaussian. White noise is actually in that class of probability measures, and the spectral gap inequality in our scaling, so using that this stray field interaction actually induces some anisotropy in the model. If you work out the dimensionality, the effective dimensionality, one can show that the law of the law brackets that satisfies the spectral gap inequality is actually supported on the space of negative Hölder distributions with regularity -5/4 minus epsilon. Now, let me point out some problems that one has to face when discussing that energy functional. First of all, if you look at the Euler-Lagrange equation of the energy, then you see that due to the nonlinearity and the roughness of the noise, it is a singular stochastic PDE. And the first existence theory, at least for small noise, so for small values of the parameter sigma I introduced before, has been worked out by Ignat and Otto using a Prato-Debush type approach and Wigner normalization to give sense to the nonlinear term, the problematic nonlinear term. We actually want to study a large noise regime. That is, we don't want to assume any smallness on the parameter sigma, and for the rest of the talk, just think of sigma being equal to 1 for simplicity. And we do this by employing a variational approach that is based on the direct method of the calculus of variations. Note, however, that since the energy function is non-convex, we cannot expect that minimizers are almost surely unique. So the universality of the magnetization ripple is actually better expressed on the level of the energy itself, which I printed here again. But actually, let me point out that if you look at a function v, which solves the linearized Euler-Lagrange equation, then it turns out that the total energy of that v is almost surely minus infinity, at least under the law of white noise, which is somehow the model we want to reach in the end. So at that point, one could say, well, okay, that's the end of a variational approach, but it turns out to be not that bad, because that's the only problematic infinity somehow in this energy. If we subtract this infinity and go to renormalized energy, then it turns out to be doable. So an analysis based on the direct method of the calculus of variations turns out to be doable with this renormalized energy, which for convenience I split into two parts. One is an anharmonic energy type term and a remainder. And actually the main deterministic analysis, the main interesting point in the deterministic analysis of our problem is to make use of some subtle cursivity that comes from the Burgers operator that somehow is in this anharmonic energy. And we do this, as I pointed out before, by using some identities for the inviscid Burgers equation and also some Schauder tools for non-local equations, because the linearized equation contains a non-local anisotropic but elliptic operator. However, we still have the problem that using the law of white noise, the product VR1D2V, V again a solution of the linearized equation, turns out to be not well defined. For this, we impose a renormalization rule, which in the Gaussian setting is actually Wigner normalization. But now, since we're not in the Gaussian setting, our probabilistic analysis has to rely on the spectral gap inequality to handle these non-Gaussian noises. And the main result somehow could be phrased in the following way. Using the topology of gamma convergence, which is quite natural in our situation because we want to consider minimizers, sequences of functionals, looking at these minimizers and have that these sequences of minimizers converge again to minimizers of the limiting functional. So using the topology of gamma convergence on the space of lower semi-continuous functionals, we're able to give a sense to the law of the renormalized energy in such a way that it is independent of the way we approximate white noise, at least in this class of probability measures satisfying the spectral gap inequality and the centeredness, stationarity, and symmetry assumptions. More precisely, if we have these assumptions, then taking such a probability measure, we can extend it to a probability measure on the product space of distributions and lower semi-continuous functionals that naturally we want to endow with the topology of gamma convergence in such a way that the first marginal of this extended measure is given by the one we started with. If the original measure happens to be concentrated on smooth functions, then the energy under this extended measure is actually given by, or almost surely under this extended measure, given by the renormalized energy with V and parameter V R1 D2V, which is now well defined because Xi is almost surely smooth. And we have a continuity property if we take a sequence of ensembles that converges weakly to a limiting ensemble, then also the extended ensembles on the space of X's and energy functionals converges weakly to the extension of the limiting measure, and that is the universality of the ripple. Since I don't have much time, this is essentially the strategy we employ to prove it, which is very analogous to a rough path approach, namely we take our noise Xi, but since we have the problem that we cannot associate the total or renormalized energy to that object because it's too rough, we extend the space of data by our renormalization, which is analogous to the extension of Brownian motion by its first iterated integral. We lift our distribution brackets to this space of enhanced data, and then use our deterministic analysis to prove that the map that associates to each triple CVF, where F can be thought of the V D2R1V, the ill-defined term. So we look at the map that maps this CVF to a renormalized energy and can show with our deterministic analysis that this map is continuous with respect to the topology induced by gamma convergence, and therefore are able to give sense to the law of to this extension measure that I showed you on the slide before. So that is the way we define this lift of the measure, the original measure, to the space of X's with energies, lower semi-continuous energy functionals. And yeah, I think I more or less reached the end of my time. So let me thank you very much for your attention.